Welcome to our webinar, and we're going to begin with a welcome from Bill Sutton.
Thank you so much, Pat. Hello and welcome. On behalf of the Energy 2.0 Society, I'd like to greet you to our first webinar. I am Bill Sutton. I'm a board member here at the Energy 2.0 Society. And so this webinar will feature three presenters whose experience closely relates to the subject of low energy nuclear reactions. I'd like to thank them in advance. They're graciously sharing their time and opinions today with us in this forum. I'd also like to thank all the people that are joining us as participants in the webinar. As we looked over the registrations, we noticed it was a widely diverse group of people from all over the globe who have registered and have an interest in this webinar. So thank you. For those of you that have seen the Energy 2.0 website, you know that our organization is primarily educational in its mission. In the past, we've had guest lecturers go out from our board and make presentations. And you'll find some of those on the website, and they serve as a good introduction to the subject of LENR. It's our goal and intent, though, is to identify a method to demonstrate LENR as a practical means of producing heat and electricity, make those results open to the public, and to supply research labs with demonstration kits for their use. However, replication to date has been somewhat of an elusive target. As more is known and released, the home replicator will have a better chance of producing a successful trial. It's our goal to make the process well known and to put the process within reach of the public for adaptation. So we do anticipate future webinars so as to reach these goals. I will now turn the mic back over to Pat Higbee, who is from the University of Northern Iowa.
So now we're going to move over to the introduction of speakers by Frank Ackland.
All right, well, we've got a good lineup of speakers today. We're going to be starting out with Dr. Vladimir Dubinko, who is leading researcher at the National Science Center at the Kharkov Institute of Physics and Technology in Kharkov, Ukraine. And Vlad will be talking about local anharmonic vibrations in crystals and clusters with applications to LENR.
Very good. So I now announced the title Quantitative Model of ECAD based on the LAV theory. By quantitative model, I mean that I would like to present you some clear logic from the very fundamental laws of physics, and mind you, conventional physics. I'm not going to invent any new principles in contrary to the majority of scientists working in the LENR field. One of my main arguments is that the known physics is quite sufficient for us to understand the principles of LENR. And the other message will be that probably we will not going to reach the control over LENR without understanding its physics. So we will discuss a little shortly some replications like Rossi, Parkhomov, Nikaseyka, and then to proceed with some short theory on why it's so difficult to tunnel through Coulomb barrier at low temperatures. And actually we will try to find the way out of this difficulty, introducing new concept of discrete breathers. It's not a new concept for solid-state physics or for mathematics, but to the field of LENR, it's kind of a new thing. And then we try to understand how this concept will help us to tunnel through the colon barrier and actually to build some quantitative estimates of the operation of energy generators. So the first slide is very well known replication, actually experiment by Rossi, which is claimed to produce kind of a kilowatts of energy, excess energy per gram of the fuel, which is composed mainly from nickel and hydrogen. Also, lithium is seems to be an important ingredient. And after Rossi, and especially after the replication by Parkhomov, a lot of researchers tried to reproduce this experiment, but only a few of them have been successful. And that the principal question is why, in spite of the fact that all try to imitate the same conditions, some of them are successful and some of them are not. For instance, I was a witness of successful replication by Nika Seika in Kiev, which is the capital of Ukraine, and in his replication, can be clearly said that you see the reactor setup. It's just heating some vessel with reactor, let's say, with this fuel, very closely imitating the Parkhomov setup. But the difference is that the temperature is very, very good controlled at, in this particular case, at 1000 of Celsius. And then one can compare between the energy consumption of the test specimen with no fuel and with the loaded fuel. And you can see on the bottom part of this slide that the test, the control specimen shows the energy consumption 180 watt, while the loaded one shows the consumption of 140, which means that at least 40 watt difference is produced in this reactor. And the question is why? Other replicators, like for instance Jean Beverian or from France, or Budko and Korshunov from Moscow, and many of others didn't succeed in spite of the very close approach to the problem. To my mind, the answer lies in the material, in the microstructure of the specimens. But to understand that, first let us shortly consider the underlying physics. And of course, the most difficult problem we are facing is penetration or tunneling, as physicists call it, through the Coulomb barrier, which prevents any nuclear reaction from being started. And it is very well known that at room temperature, the probability to penetrate through the Coulomb barrier is 10 to minus 2000 something, which is practically zero. And so a lot of theoretical attempts were directed at screening of the Coulomb barrier by, for instance, electrons. This slide shows you the plot of the tunneling coefficient, this probability of tunneling, as a function of the tunneling distance. And the idea is that if we, by some mechanism can bring the nucleus, for instance, of two deuterons at the distance of 1 angstrom, like here, then you will see that by gamma formula, the probability of tunneling is 10 to minus 100, which is 0. If it is possible to screen this barrier up to the distances of just a few fractions of angstroms, then the probability increases drastically. But in order to achieve 10 to minus 12, which is still very, very low quantity, but in principle it could explain some of the experiments, you need a distance, screening distance, just 1% of an angstroms, which is too small for electrons. Electrons are far, far away as compared to these distances. That's why all the traditional physicists don't believe in this mechanism. And so, to my mind, the answer lies in the well-forgotten, but nevertheless very well-established principles. These principles were established by Schrödinger and Robertson, who actually modified the very well-known uncertainty relation by Heisenberg. Heisenberg relations looks like this. This is a product of uncertainty between one quantity and another. For instance, momentum and distance and coordinate. And on the right side, this is some operators. When you resolve this algebra, you will get something like this. This product is more than a Planck constant. But if you take into account the correlation between these operators, then you will result with this correction. And usually, if there is no correlation, of course, you have the same result, and the same result which was obtained by gamma. So if you take into account this correlation coefficient, then we can really modify the gamma formula, and then the probability, at least in principle, can be increased enormously. So the question is, can the correlations make the barrier practically transparent? And the principal answer is yes, and this plot shows you why. It shows you the distribution of the probability of a particle to be somewhere inside or outside the potential well. So if there's no correlation, it is localized. It is strongly localized within the potential well. But when the correlation appears, it becomes delocalized, as the lower part shows you, which means that somehow there's a high probability of the particle go under the barrier, and if the barrier ends at some point, some angstroms away, in principle, it can penetrate through the barrier. And the physicist from Kiev, Vladimir Vysotsky, actually discovered the way to increase the correlation coefficient. And this way consists in modulation, oscillation of these potential well widths. So it's kind of a vibrating potential well. So if you can vibrate this potential well, make it oscillate, then just pure mathematics shows you that the correlation factor increases and becomes very close to unity. And the main question following from the V theory is, what is the physical mechanism of this potential well oscillation? What we need is, for instance, these three atoms oscillating like this. One of the atoms should oscillate with a very large amplitude as compared to usual amplitudes of phonons. and thus making his neighbors, let's say, to experience these oscillations of the potential wells. And but why? So my message is, all you need to understand it is LIV. LIV is a localized anharmonic vibrations, actually discovered in 1969 by Ovchinnikov, who showed us that already two coupled oscillators can be more or less independent from each other, which means that they don't share energy. Now, with a very, very sophisticated tools, we can show that, for instance, in iron, we can model by MD modeling these LIV, these vibrating atoms, as you see in this animation. And it can be either standing or mobile, like in this one. So when we come, for instance, to the deuterated palladium, then you will know that the structure of it is the same as the rock salt, with the heavy and light atoms interchanging. And due to the difference of masses, there is a gap in the phonon spectrum. And in this gap, you can excite the LIV. Not going into details, it's possible to construct the picture of the density of states of the vibration modes of this crystal, which actually can make what we call the parametric resonance, when the frequency of the oscillation of the potential well equals the cell frequency multiplied by 2. If this is so, then the tunneling coefficient from the starts to increase with increasing number of the oscillation cycles enormously, from 10 to minus 100 and less, practically to unity. That's the leading idea. But now, preliminary conclusion is that this LIV, localized anharmonic vibrations, can result in guided increase of Coulomb barrier transparency. And the calculations show that we don't need for these super short distances. Just oscillation of 10% from the lattice spacing can be enough, provided that the lifetime of these vibrations is long enough, about, for instance, 100 of cycles, which is just 10 picoseconds actually. And based on this understanding, we can construct the rate theory of LENR, which can be compared either with excess heat production under the electrolysis of heavy water or under the conditions of ECAT by Rossi, Parkhomov, and others. For instance, in the first case, there is a quantitative comparison between the model which occurs and the experimental points provided by different researchers. And from this picture, you can see that LIV can provide up to 10 to 14 successful low-energy nuclear reactions per second in the case of heavy water electrolysis. The most important for us, for the replicators of ECAT, is the effect of temperature, because this slide shows you that this excess power production per mass, per 1 gram, yeah, it depends on the temperature kind of monotonously. And the red line shows you the effect of pure temperature. If you apply electric current, like in electrolysis, you can produce more and more LIVs. That's why the reaction rate increases. But in ECAT installations, in principle, it is possible to produce LIVs by pure heating. But you see, if you have a look at this curve already at 600 of K, you have a prediction from this very simple model of excess energy production exceeding 10 of kilowatts, which is much more than is observed by experimentalists. And the answer, the explanation of this discrepancy is very simple, because the model doesn't take into account the second effect of temperature. The first effect of temperature is to help LAV to rise, to be excited. And the second effect of the temperature is that efficiency of LAV for the tunneling is decreased, because fluctuating barrier is not as easily can be tunneled through, not as easily as a stable. So the barrier should oscillate time periodically. Then it's okay. If you have this white noise, which is caused by the temperature, it's not so okay. So at least our expectation is that the temperature dependence can be non-monotonous. That's why we need some other ways of stimulation, of triggering of LENR. For instance, in this experiment by Letts and Hagelstein, they demonstrated that you can somehow help facilitate the reaction by applying the terahertz laser frequencies. And these terahertz frequencies actually lies very near the phonon bands. So it is some coincidence, some resonance with the LAV frequencies, to my mind. And so the questions are, where and how to look for these nuclear active environments and how to trigger LENR. The first question can be answered that small energy gap is required to excite LIV. And then you can produce this nuclear active environment. And some examples are already known from MD simulations of very small nano-size nickel particles. In this picture, you see different colors and sizes of the circles correspond to the different amplitudes of atoms. And you see that some atoms or chains, small chains of atoms lying along the grains, along the surface, are really excited. And this is a molecular dynamic verification of the idea of LAV, if you will. Okay? So then the last question is how to trigger LENR. And again, the one example is to use some excitation in the terahertz diapason, and as has been done by Hagelstein and Letts. And the other is to try electron beam as the source of displacement of atoms from their equilibrium positions, and these displacements can be tuned due to the varying of the energy of the electrons. And this picture shows you the plot of our installations that we would like to build if we are funded, let's say, because it's not a very simple thing to do, but it's in principle it can be realized. And this is one of the ways, to my mind, to approach this problem from the side of deep science. In conclusion, I would like again to stress that the present results are based only on the known physical principles and on the actually independent atomistic simulations of LAVs in metals and ionic crystals. And our outstanding goal is to suggest new ways of engineering the nuclear active environment and which help to create LIVs by maybe special dopings and or some mechanical treatments and also to suggest new ways of triggering LENR. Thank you for your attention.